MS Ramaiah University of Applied Sciences.
Hi students, let us discuss the experiment on electronic circuit analysis. Aim of the experiment is to verify superposition theorem, Thevenin's theorem and maximum power transfer theorem. A regulated DC power supply is built using a rectifier circuit, a regulator circuit, many RLC components, control circuit to vary the DC voltage. When such a power supply is used in any experiment to power up any circuit, the internal details of the power supply are not needed, but the voltage that it provides and its internal resistance are alone required. This implies requirement of Thevenin's theorem. Similarly, theorems called superposition and maximum power transfer are helpful in electronic circuit analysis. Basic theorems of electronic circuit analysis help to simplify analysis of circuits with larger number of components or elements. To analyze a circuit with more than one source, superposition theorem is employed. The theorem states that voltage across any element is the sum of voltages due to individual sources. Similarly, current flowing in any circuit element is the sum of currents due to individual sources. A circuit with many resistors can be equivalently reduced to a circuit with either one voltage source in series with a resistor or one current source parallel to a resistor. The former reduction is Thevenin's theorem and the latter is Norton's theorem. Maximum power transfer theorem states that in any circuit, maximum power will be delivered to the load only if the load resistance is equal to the source resistance. If the source has complex impedance, the load impedance should be conjugate of the source impedance for maximum power to transfer to the load. The apparatus required to conduct the experiment are DC regulated power supply, decayed resistance box, breadboard and 4 resistors of 1K, 2 in number as voltmeter and ammeter. The circuit diagram for verification of superposition theorem is as shown in figure. The circuit diagrams for verification of Thevenin's theorem are as shown. The circuit diagram for verification of maximum power transfer theorem is as shown in the figure. Procedure for verification of superposition theorem. Connect the circuit as shown. Measure the currents in all the 3 resistors. Notate them I1, I2 and I3 respectively. Connect 10 volt supply and short the 15 volt supply. That is, remove 15 volt and connect R3 across R2. Measure the currents in the circuit and call them I11, I12 and I13. Connect 15 volt supply and short the 10 volt supply. That is, remove 10 volt and connect R1 across R2. Measure the currents in the circuit and call them I21, I22 and I23. Verify that Ij is equal to I1j plus I2j, where j is equal to 1, 2 and 3. Calculate theoretical values of I1, I2 and I3. Tabulate theoretical and experimental values of I1, I2 and I3 in the table shown. Procedure for verification of Thevenin's theorem. Connect the circuit as shown. Connect load RL across two 2' terminals and measure the current through the load IL and voltage across the load VL. Calculate Thevenin voltage VTH and Thevenin resistance RTH as 5 volt and 1.5 kilo ohm respectively, and connect the Thevenin's equivalent circuit as shown. Find the current through the load resistor IL and find voltage across the load resistor VL. Verify that IL is equal to IL dash and VL is equal to VL dash. Procedure for verification of maximum power transfer theorem. Connect the circuit as shown. Vary RL from 500 ohm to 2.5 kilo ohm and tabulate corresponding load current IL. Calculate load power for each RL value. Observe the peak power and corresponding RL from the table. Call this RL value as RLG. From Thevenin's equivalent circuit, it is clear that RTH is equal to 1.5 kilo ohm. Verify that RLG is equal to RTH. Tabulate the voltage and current readings for RL values from 500 ohm to 2.5 kilo ohm and calculate power for each value of RL.
Hi students, the name of the experiment is electronic circuit analysis. The aim of this experiment is we are going to verify superposition theorem, Thevenin's theorem and maximum power transfer theorem. The apparatus required for this experiment are: this is DC regulated dual power supply. This is switch on and off button. It has two power supplies, power supply 1, power supply 2. In each power supply, we have voltage control, coarse, fine, current setting, positive terminal, negative terminal. Coarse control is used to change the voltage in large steps. Fine is used to change the voltage in small steps. Current setting is kept at the maximum to avoid any accidental hazards in the circuit. Plus terminal, minus terminal are connected to positive and ground appropriately. Same connections are there here also. In this experiment, we will use both the power supplies. Decayed resistance box. This is a decayed resistance box. It is shown as positive, negative. These are the two terminals of the resistance. Any terminal can be connected anywhere. This knob is used to set resistance in steps of megaohms, multiples of megaohms. This is used to set in multiples of 100 kiloohms. This knob is used for 10 kiloohms multiples. This is for multiples of 1 kilo ohm. This is for multiples of 100 ohm. This is multiples of 10 ohm. This is multiples of ohm. Depending on the resistance value, we will adjust one or more of these knobs to proper setting. Breadboard. In a breadboard, this starting from this hole till here, all these are connected in series. Starting from here to here, one more line has all series connection. Similarly, these two lines represent one each. In these two, we have 1 to 5 connected in series. So in each column, all the 5 are connected. Here also, in each column, all the 5 are connected. Based on the settings, connection settings, we have to use appropriately. 1 kilo ohm resistors. These are resistors. We are using 4 1 kilo ohm resistors in this experiment. Connecting wires. These are connecting wires. We will use these wires to connect components on the breadboard. Voltmeter, ammeter. These are multimeters. In this experiment, we will use one as voltmeter, one as ammeter. In each multimeter, we have adjustments for voltage readings and current readings. We have to set the knob, this off position knob, appropriately for measuring current or voltage. We will use it for DC voltage and DC current measurement in this experiment. Let us start the experiment for verification of superposition theorem based on the circuit diagram. Superposition theorem requires two sources, I am connecting from plus terminal of source 1 to anywhere on this breadboard. I am connecting here. Negative terminal I am connecting here. Take the connecting wire from plus terminal of second source. This is connected here. Take one more connecting wire from negative terminal of second source to this place. This place we have already connected negative terminal of source 1. Same place negative terminal of source 2 should be connected. Now take 1 kilo ohm resistor, connect it from plus of first source to a position somewhere here. Take one more 1 kilo ohm resistor, connect from this 1 kilo ohm resistor to source 2. Positive terminal of source 2. Take one more 1 kilo ohm resistor, connect from this joint of resistors to negative supply, negative terminals of both the sources. So resistor 1, resistor 2, resistor 3. Connections for superposition theorem are completed. Before switching on the power supply, we have to put voltage in the minimum, current in the maximum. Voltage in the minimum, current in the maximum. Now switch on the power supply. Source 1 voltage, let it be 10 volts. Source 2 voltage, let it be 15 volts. Now take ammeter, put this in DC current reading. Let the setting be in 20 milliamps. Now let us measure currents in all the three resistors. Let us measure current in first resistor. Remove the wire. Put it in nearby hole. Measure current between this new position and the resistor's leg. The current reading is shown as 1.64 milliamps. replace this node back in original position. Same way, remove this resistor leg, measure current between this joint and the removed leg. The ammeter shows 8.36 milliamps. Replace the resistor's leg back in original position. Same way, put source to positive leg in a nearby node. Measure current in this resistor. The ammeter shows you 6.72 milliamps. If you reverse the ammeter legs, it will show 6.72 milliamps. Previously it is shown negative, now it is showing positive. Put this leg back in its original position. All the three current readings note down in a table. Now remove source 2, take a connecting wire, and short from this resistor leg to this common connection. Again measure current through 3 resistors. Similarly, put source 2 back in original position. Remove source 1. Short this resistor leg to the common terminal. Again measure currents through all the 3 resistors. So totally we have 3 sets of readings. Set 1, we have currents in 3 resistors when both the sources are present. Second set, we have currents when source 1 is present and source 2 is shorted. Set 3, we have currents when source 1 is shorted and source 2 is present. Verification of superposition theorem will show that the readings of set 1 are equal to summations of set 2 currents with set 3 currents. This completes verification of superposition theorem. Now let us start verification of Thevenin's theorem based on circuit diagram. Take a connecting wire, connect from positive of source 1 to this position. Connect from positive terminal of source 1 to this position. Take another connecting wire, connect from negative of source 1 to this common terminal. Source 1 positive terminal, source 1 common terminal. Now take 1 kilo ohm resistor, connect from source 1 positive to this position. Take another 1 kilo ohm resistor, connect from this position to this position. Take one more 1 kilo ohm resistor, connect from this joint of two resistors to common terminal. Take another 1 kilo ohm resistor, connect from the last resistor, end of the last resistor to common terminal. This completes circuit diagram for Thevenin's theorem. Now switch on the DC power supply. Set the voltage reading to 10 volts. Volts. We will measure current in this load resistor and voltage across the load resistor. Let us take ammeter, put the knob in 2 milliamps reading. Measure the current. The current is shown in the ammeter as 1.9 milliamps. Put the resistor leg back in original position. Now change the reading to voltage. Put in 20 volts. Now measure voltage across the resistor. The voltmeter is showing a voltage of 2 volts. Note down the voltage and current readings taken across the load resistor for this experiment. In this circuit, retain the load resistor and source. Remove the 3 resistors. Change the voltage reading to 5 volts. Between the two, connect DRB. Take a connecting wire, connect to positive of the DRB. Take another connecting wire, connect to negative of DRB. Set the resistance of DRB as 1.5 kilo ohms. So 1 into 1K is 1K. 5 into 100 ohms, 500 ohms. Total resistance of DRB is 1.5 kilo ohms. Connect this to source side and load side. Now we have source, then DRB, then load resistance. We are measuring now voltage across the load and current flowing in the load. Take ammeter, measure current in the load resistor. Change the knob to 2 milliamps and measure the current in the load. The ammeter shows 1.926 milliamps. Put the resistor leg back in original position. Measure voltage across the resistor. Change the knob to 2 volts. Measure voltage across the resistor. The voltmeter shows 1.986 volts. The voltage and current readings that we now got are same as the readings obtained for the previous connection. This verifies Thevenin's theorem. Now let us start verification of maximum power transfer theorem based on circuit diagram. Take a connecting wire, connect from source 1 to this position. Take another connecting wire, connect from negative terminal of source 1 to common terminal. Let common terminal be here. Take 1 kilo ohm resistor, connect from source 1 positive terminal to this position. Take another 1 kilo ohm resistor, connect from this resistor leg to common terminal. Take one more 1 kilo ohm resistor, connect from this junction of resistors to a node here. Now take DRB, connect as a load to your circuit. one terminal of DRB is here. One more terminal. Connect to common terminal. This is your circuit diagram. Now take one multimeter as ammeter. Take a connecting wire, wind it to ammeter. Take one more connecting wire and wind it to ammeter. Put the knob in 20 milliamps position. Connect the ammeter to measure current flowing in the DRB. Positive leg of the ammeter connect here. Negative leg of the ammeter connect here. Make sure your wires are intact. Take voltmeter and wind two connecting wires. Place the voltmeter across the DRB. Positive of voltmeter, negative of voltmeter. Make sure your connections and all the wires are intact. Put the voltmeter in 20 volts position. Now the DRB setting, let that be 500 ohms. Let the DRB setting be 500 ohms. Now switch on the power supply. Put 10 volts as voltage setting. as soon as the power supply is kept as 10 volts, voltage across the load, that is DRB, and current flowing in the load are available in voltmeter and ammeter respectively. Change the DRB resistance from 500 to 700. Note down the ammeter and voltmeter readings. Change the DRB to 900 and again note down the readings. Now change the DRB reading to 1 kilo ohm. So put 1 here and let this knob go to 0. So 1 kilo ohm on DRB. Again note down the readings. Change the DRB resistance to 1.2 kilo ohm and note down the readings. Put the DRB resistance to 1.4 kilo ohm. Again note down the readings. Put the DRB reading as 1.5 kilo ohm and note down the readings. Repeat this way of tabulating till the load resistance in the DRB becomes 2.5 kilo ohms. Note all the readings in the table. You will find that maximum power will transfer to the load when the load resistance is 1.5 kilo ohms. This verifies maximum power transfer theorem.
At MSR UAS, we spark your imagination unlike any other.